Biogeograph is the study of geographical distributions of organisms, their habitats and the environmental factors that produce them. Biogeographic classification of India was done by Rogers and Panwar, 1988. Within India the classification recognizes 10 zones, divided into 26 provinces. The classification was done using various factors such as altitude, moisture, topography, rainfall. Etc. Biogeographic zones are large distinctive units of similar ecology, biome representation, community and species, e.g. the Himalaya, the Western Ghats. The classification was done using various factors such as altitude, moisture, topography, rainfall, etc. Biogeographic zones are large distinctive units of similar ecology, biome representation, community and species, e.g. the Himalaya, the Western Ghats. Whereas the biotic province is the secondary units within a zone, giving weight to particular communities separated by dispersal barriers or gradual change in environmental factors, e.g. Northwest and West Himalaya either side of the Sutlej River. Biogeographic zones of India are U. 425. Life Sciences Admin. Ecology. Criteria pollutants. Criteria pollutants are those air pollutants for which ambient air standards have been defined to protect human health and welfare. Criteria air pollutants are 6 major pollutants defined by EPA, Environmental Protection Agency. These are carbon monoxide, lead, nitrogen dioxide, ozone, particulate matter, and sulfur dioxide. Carbon monoxide, CO, is a colorless, odorless, tasteless gas and the most abundant of the criteria pollutants. It is produced as a result of incomplete combustion of carbonaceous fuels. Incomplete combustion yields CO instead of CO. Vehicular emissions are the major source of CO emission. It comprises approximately 70% of total CO emissions. CO has greater affinity for hemoglobin than does O. Hence, it interferes with the blood's ability of carry O to the cells of the body. It readily binds to hemoglobin form carboxyhemoglobin. Ozone. Tropospheric ozone is a secondary air pollutant. Sources of ozone in the troposphere are both natural and anthropogenic. Natural sources are responsible for an average background surface ozone concentration of 20 to 30 ppb. Ozone is produced during the no-catalyzed oxidation of hydrocarbons. In the presence of sunlight, NOx and hydrocarbons indicate a complex set of reactions that produce a number of secondary pollutants known as photochemical oxidants. Ozone is the most abundant of the photochemical oxidants. Ozone is also a constituent of photochemical smog. Smog is a term that was derived from smoke and fog. Photochemical smog is also known as Los Angeles smog. It requires neither smoke nor fog. This type of smog has its origin in the nitrogen oxides and hydrocarbon emitted by automobiles and other sources, which then undergo photochemical reactions in the lower atmosphere. The highly toxic gas ozone arises from the reaction of nitrogen oxides with hydrocarbon in the presence of sunlight, and some nitrogen dioxide is produced from the reaction of nitrogen oxide with sunlight. Other major components of photochemical smog are formaldehyde, acrolein, peroxyacetyl nitrate, PAN, and peroxybenzoyl nitrate. The resultant smog causes a light brownish coloration of the atmosphere, reduced visibility, plant damage, irritation of the eyes, and respiratory distress. Another type of smog is sulfurous smog, which is also called London smog, results from a high concentration of sulfur oxides in the air and is caused by the use of sulfur-bearing fossil fuels, particularly coal. Oxides of nitrogen. 2 important oxides of nitrogen, NOx, that considered as air pollutant are nitric oxide, NO, and nitrogen dioxide, NO. Almost all NOx emissions occur in the form of NO. NO can oxidize to NO. NO may react with hydrocarbons in the presence of sunlight to form PODC. Chemical smog. NO also reacts with O radical to form nitric acid, HNO. Pipe. Particulate matter. Atmospheric particulate matter is defined as solid or liquid dispersed matter which is smaller than about 500 ohm. Particulate matters which are less than 10 microns in diameter are known as PM10. Solid particles are termed dusts if they are generated by grinding or crushing operations. Solid particles are called fumes if they are formed when vapors condense, whereas liquid particles may be called mist. Smoke and soot are terms used to describe particles composed primarily of carbon that result from incomplete combustion. Sulfur dioxide. Major source of sulfur dioxide emissions are the fossil fuel combustions. Sulfur dioxide, once released, can be converted to SO, reacts very quickly with water to form sulfuric acid, which is the principal cause of acid rain. Lead is emitted to the atmosphere primarily in the form of inorganic particulates. Most lead emission occurred in the past from motor vehicles as a result of burning of gasoline containing the anti-knock additive, tetrathiene. Lead. Life Sciences Admin. P. E. S. R. E. Y. T. R. T. N. MU. XETPR. S. E. Ecology. Air quality standards. EPA has established 2 levels of national ambient air quality standards, primary and secondary. Primary standards are required to be set at levels that will protect public health including the most sensitive individuals. Secondary standards are established to protect public welfare, e.g., crops, animals, structures. Secondary standards are meant to be more stringent than primary standards. Greenhouse effect. Various gases in the atmosphere absorb incoming short-wave solar radiation and long-wave or thermal radiation radiated by Earth. The ability to absorb radiation depends on the wavelength. All of the incoming solar radiation with wavelengths less than 0.3 ohm is absorbed by oxygen and ozone. This absorption occurs in the stratosphere. Most of the long wavelength radiation greater than 4 pump radiated by Earth is absorbed by atmospheric gases, most importantly water vapor, Colorado, N, O and CH. Outgoing radiation between wavelengths 7 and 12 pm easily passes through the atmosphere. This region is referred to as the atmospheric radiative window. Radiatively active gases that absorb wavelengths longer than 4 pm are called greenhouse gases. These gases absorb most of the outgoing thermal radiation attempting to leave the Earth's surface. This absorption heats the atmosphere, which in turn radiates energy back to the Earth. These greenhouse gases act as a thermal blanket around the Earth, raising the Earth's temperature. This effect is known as greenhouse effect. The greenhouse effect is a natural phenomenon. It is responsible for Earth having an average near-surface air temperature 33 degrees Celsius warmer than it would have if it did not have greenhouse gases in the troposphere. Figure 7.26. Greenhouse gases trap long-wavelength energy from the Earth's surface, heating the atmosphere, which, in turn, heats the Earth. Kyoto Protocol. The Kyoto Protocol is an international agreement linked to the United Nations Framework Convention on Climate Change. The protocol was adopted in Kyoto, Japan, on the 11th of December 1997 and entered into force on the 16th of February 2005. The Kyoto Protocol is a legally binding agreement under which industrialized countries will reduce their collective emissions of greenhouse gases by 5.2% compared to the year 1990. The goal is to lower overall emissions from 6 greenhouse gases: carbon dioxide, methane, nitrous oxide, sulfur hexafluoride, hydrofluorocarbons and perfluorocarbons. Global warming. Global warming is defined as the increase in the average temperature of the Earth. Over the last 100 years, the average temperature of the air near the Earth's surface has risen a little less than 1 degree Celsius, 0.74 equals 0.18 degrees Celsius. The rate of warming over the last 50 years has almost doubled that for the period 1906. 429. Life Sciences Admin. Ecology. 2005 as a whole. Increasing greenhouse gas concentrations resulting from human activity such as fossil fuel burning and deforestation is mainly responsible for the observed temperature increase. An increase in global temperature will cause sea levels to rise and will change the amount and pattern of precipitation, probably including expansion of subtropical deserts. The continuing retreat of glaciers, permafrost and sea ice is expected, with warming being strongest in the Arctic. Other likely effects include increases in the intensity of extreme weather events, species extinctions, and changes in agricultural yields. Stratospheric ozone. Stratospheric ozone formation. The process of ozone formation in the stratosphere first involves the formation of atomic oxygen, O, from the photolytic decomposition of molecular oxygen, 0. 0 plus Hv less than 242 nanometers, 0 plus O. The atomic oxygen, in turn, reacts with molecular oxygen to form ozone. 0 plus 0 plus M, O, plus M, where M represents a third body, N, or O, necessary to carry away the energy released in the reaction. The ozone that is formed in this process is also dissociated by solar radiation to form an oxygen atom and an oxygen molecule. Ozone absorbs UV radiation in the 200 to 320 nanometers wavelength region and generates molecular oxygen as a result of photodissociation. O plus Hv, 0 plus O. This cyclic process leads to a natural steady-state concentration of stratospheric ozone. These three reactions are called the Chapman cycle, after the person who discovered them. Levels of ozone are measured in Dobson units (du). The average amount of stratospheric ozone throughout the world is about 300 du. Ozone concentrations over Antarctica during the period of greatest depletion usually fall well below 200 du. Stratospheric ozone depletion. Ozone is continuously being synthesized from molecular oxygen in the stratosphere by the absorption of short-wavelength ultraviolet (UV) radiation, while at the same time it is continuously being removed by various chemical reactions that convert it back to molecular oxygen. The rates of synthesis and destruction at any given time determine the concentration of ozone in the stratosphere. This balance is being affected by increasing stratospheric concentrations of chlorine, nitrogen, and bromine, which increases the destruction process. The most prominent type of ozone-destructive gases are the chlorofluorocarbons, CFCs. The possibility of stratospheric ozone depletion caused by CFCs was proposed by F. Sherwood Rowland and Mario Molina. CFCs are inert molecules and have residence times of over 100 years in the troposphere. These gaseous molecules diffuse through the troposphere to the stratosphere. In the stratosphere, CFC molecules can be broken by ultraviolet radiation, freeing the chlorine. The chlorine freed in the reaction acts as a catalyst in the ozone removal process. A single chlorine atom may break down thousands of ozone molecules before it returns to the troposphere. After chlorine is released from CFC, it reacts with ozone to form chlorine monoxide, CiO, which reacts with NO, to form chlorine nitrate. Cl plus 0, Cl plus O. Cl0 plus NO, CiONO. AN. Life Sciences Admin. Orology. Compounds such as CiONO hold chlorine in an inactive form and collectively called reservoirs. They can release inactive chlorine in the presence of sunlight. Antarctic ozone hole. The Antarctic ozone hole is limited in space and time, occurring at the time of year when the sun first appears above the horizon after the long polar night. In the Antarctic winter, a unique atmospheric condition, known as the polar vortex, forms. The polar vortex blocks warmer mid-latitude air from mixing with the air above the pole, creating extremely cold polar air temperatures. Stratospheric temperatures may fall below -90 degrees Celsius, which is cold enough to form polar stratospheric clouds even though the air is very dry. In this cold vortex, polar stratospheric ice crystal clouds form. This unique atmospheric condition eventually allows the chlorine to be released from chlorine nitrate. The ice crystals that make up polar clouds provides the reaction surfaces where chlorine nitrate reacts with water to form hypochlorous acid, HOCI. H, 0 plus CiONO, HOCI plus HNO. As soon as the sun rises in the Antarctic in August, chlorine stored in HOC is freed by photolysis. HOCI plus CHV, Cl plus O. The freed chiarine causes destruction of ozone. Ozone densities drop rapidly, only to recover when the polar vortex breaks up, mixing warmer air in and releasing the ozone-depleted air to move away from the polar region. Effect of ozone depletion. Since the ozone layer absorbs a great quantity of the harmful ultraviolet radiation present in sunlight, the amount of harmful ultraviolet radiation reaching ground will increase if the ozone layer is depleted. Increased ultraviolet radiation will affect the health of humans and the ecosystem. Ultraviolet exposure can cause skin cancer, cataracts, and impaired immunity systems, as well as a loss of balance in the vegetation and hydrosphere ecosystems. Montreal Protocol. The Montreal Protocol on substances that deplete the ozone layer is a landmark international agreement designed to protect the stratospheric ozone layer. The treaty was originally signed in September 1987 and became effective in 1989. The Montreal Protocol stipulates that the production and consumption of compounds that deplete ozone in the stratosphere, chiarofluorocarbons, CFCs, halogens, carbon tetrachloride, and methyl chloroform, are to be phased out by year 2000. Acid rain. Acid rain is a broad term referring to a mixture of wet and dry deposition from the atmosphere containing higher than normal amounts of nitric and sulfuric acids. Rainwater is naturally acidic, pH of about 5.5, in nature as a result of the reaction of water vapor, carbon dioxide and nitrogen in the atmosphere. The acidity increases through the introduction of sulfur dioxide and nitrogen oxides into the atmosphere from both natural sources, such as volcanoes and decaying vegetation, and man-made sources primarily from fossil fuel combustion. Acid rain occurs when these gases react in the atmosphere with water, oxygen, and other chemicals to form various acidic compounds such as sulfuric acid and nitric acid. Acid rain usually has a pH of less than 5.5. The term acid rain is used most often, but acid precipitation is more accurate since it can also reach the ground as dry particles in dust and smoke. Acid rain causes acidification of soil, lakes, streams, and damage of plants. In addition, acid rain accelerates the decay of building materials. Prior to falling to the earth, and NOx gases and their particulate matter derivatives, sulfates and nitrates, also cause harm to the public health. 431. Life Sciences Admin. Ecology. Water pollution. Water pollution refers to the changes in the physical, biological, and chemical conditions of any body of water which can be harmful to organisms and plants that live in these water bodies. Water pollution has many sources. The sources of water pollution may be point and diffuse sources. A point source is a single identifiable focalized source of water pollution. Point sources of water pollution include municipal sewage treatment plant discharges and industrial plant discharges. Non-point source pollution or pollution from diffuse sources generally consists of polluted runoff from farmland and mines, forests, land development and other activities. There are many causes of water pollution, some natural, some man-made. Some of the major agents of freshwater pollution are industrial discharges, runoff from farmland and mines and sewage. Pollutants coming from chemical and industrial processes are TT, major cause of water pollution. When factories and manufacturers pour their inorganic and organic wastes directly into streams and rivers, the water becomes poisonous and oxygen levels are depleted, causing many aquatic organisms to die. The heated water from the industries also cause thermal pollution. This killed aquatic animals and plants by reducing the oxygen content of the water. Another cause of water pollution is polluted runoff from farmland and mines. Farm pesticides, chemical fertilizers and organic wastes pollute the water bodies. One more cause of water pollution is sewage coming from households. Effects of water pollution. The effects of water pollution are not only devastating to human but also for animals. Polluted water destroys aquatic life and reduces its reproductive ability. Polluted water is unsuitable for drinking, recreation, agriculture, and industry. It diminishes the aesthetic quality of lakes and rivers. Biochemical oxygen demand and chemical oxygen demand. The amount of dissolved oxygen used up by aerobic microorganisms to decompose the organic matters present in a sample of water is termed biochemical oxygen demand or biological oxygen demand (BOD). 1T is an indirect measure of the readily biodegradable organic matters. Since aerobic microorganisms live by decomposing organic matters, hence the amount of oxygen used is proportionate to their Humber and metabolic rate. BOD test evaluates the dissolved oxygen used up by aerobic microorganisms over a 5 days period at 20 degrees Celsius. BOD concentration of a wastewater expressed in milligram per liter. BOD of clean fresh water is 2 milligrams per liter, whereas value exceeding 5 milligrams per liter indicate contamination. When BOD levels are high, there is a decline in DO levels. Chemical oxygen demand (COD) is used as a measure of oxygen requirement of a sample that is susceptible to oxidation by strong chemical oxidant. Under controlled conditions of TMA and temperature, a chemical oxidizing agent, potassium permanganate or dichromate, is added to the sample of water, and the amount needed to oxidize the reducing materials present is measured. From this, the chemically equivalent amount of oxygen can be calculated. Since the reducing substances typically include remains of living organisms, COD is regarded as reflecting the extent to which the sample is polluted. Bioaccumulation and biomagnification. Bioaccumulation is the storage of chemicals in an organism in higher concentrations than are normally found in the environment. For example, DDT, a fat-soluble chemical, may be present in the environment in small quantities, but biological activity concentrates it in the organism. Biomagnification is the accumulation of chemicals in organisms in increasingly higher concentrations at successive trophic levels. Consumers at higher trophic levels ingest a significant biomass present at lower levels, along with the fat-soluble pollutants stored in their tissues. Biomagnification occurs in both aquatic and terrestrial habitats. Life Sciences Admin. Ecology. Eutrophication. Eutrophication is a process whereby water bodies, such as lakes, ponds, receive excess inorganic nutrients, maintain nitrogen and phosphorus-containing compounds that stimulate excessive algal growth, often called an algal bloom. Nutrients can come from many sources, such as fertilizers applied to agricultural fields and sewage treatment plant discharges. Eventually, the death and decomposition of algae reduces dissolved oxygen in the water. Depending on the degree of eutrophication, subsequent negative environmental effects such as anoxia and severe reductions in aquatic animal populations may occur. Eutrophication is a natural phenomenon. Natural eutrophication is a process that occurs to all lakes over time, as the weathering of rocks and soils from a surrounding catchment area leads to an accumulation of nutrients and associated sediments in the water. Lakes can be categorized on the basis of their richness in nutrients, which typically affects plant growth. Oligotrophic lakes. These lakes are nutrient-poor and biologically unproductive lakes. Mesotrophic lakes. Mesotrophic lakes contain moderate amount of nutrients. These lakes are biologically productive. Eutrophic lakes. Eutrophic lakes are very rich in nutrients and biologically very productive. High nutrients concentration result in excessive growth of phytoplanktons, algal bloom, and low oxygen levels and undesirable water quality. Soil pollution. Soil pollution, also commonly known as swath contamination, is a condition that occurs when soil loses its structure, biological properties and chemical properties due to the use of various man-made chemicals and other natural changes in the soil environment. Occurrence of soil pollution is correlated with the degree of industrializations and intensities of chemical usage. Various human activities are causing the soil pollution. These activities are deposition of oxides of sulfur and nitrogen, the oxides of sulfur and nitrogen, chlorides, fluorides, etc. emitted into the atmosphere due to combustion of fossil fuels from vehicles and various industries come down as dry or wet deposition, acid rain, onto the soil and lower the soil pH. Use of pesticides, insecticides and herbicides. Various pesticides, insecticides and fungicides used in agriculture practices causes soil pollution. Similarly, herbicides used for weed control in agricultural practices affect biological properties and chemical properties of soil. These substances pollute the soil depending upon their volatility, biodegradability, persistence, leaching, chemical reactivity and absorption on the soil particles. Release of sewage matters and use of chemical fertilizers. Sewage matter is commonly used as fertilizer or deposited as waste on the soil. Decomposition of sewage may release various toxic heavy metals that cause increase in heavy metal toxicity. Detergent substances may also be released from sewage causing damage to soil. Chemical fertilizers are generally used far in excess of the requirements of the crop. The unutilized fertilizers cause soil pollution. Deposition of industrial effluents and solid wastes. Various inorganic and organic substances are present in the industrial effluents. They affect various soil characteristics. Effluents affect the mineral structure, soil pH, exchangeable base status, etc. of the soil. Large quantity of solid wastes like unused and rejected chemicals like calcium carbonate, magnesium sulfate, ferrous chloride, ferrous oxide, radioactive wastes, fly ashes, sludge, plastic materials, unwanted industrial wastes generated during manufacturing processes, rejection, broken items of metal, plastic, wood and or chemical solids, powders are dumped over on the surface of soil. All these solid materials dumped on surface of soils are bound to change the chemical in. Logi. Physical nature of soil besides contributing large quantity of pollutants to underground water whenever and water passes through them. Dioactive pollutants. A variety of radioactive waste materials like strontium-90, cesium-137, iodine-131, etonium, uranium, neptunium, etc. or added to soil from nuclear activities. These substances may be etched into water or may be directly added to water that is used as coolant in nuclear power plants. Control of soil pollution. Control measures for soil pollution and land degradation involve safer and use, planned urbanization, controlled developmental activities, safe disposal and management of solid wastes from industries and human habitations, afforestation and reforestation. Management of solid wastes involves collection and categorization of wastes, recovery of resources like scar metals and plastics for recycling and reuse, safe hyposols with minimum environmental hazards. ELF test. L. Which of the following is incorrectly paired with its description? A. Neritic zone shallow area over continental shelf. B. Abyssal zone benthic region where light does not punctuate scent. Littoral zone area of open water. D. Intertidal zone shallow area at the edge of water. A type 1 survivorship curve is characteristic of a species with a rapid increase in mortality in old age. This type of curve is A. Typical of many invertebrates that produce large number of offspring. B. Typical of humans and other large mammals. C. Almost never found in nature. D. Typical of all species of birds. All of the following characteristics are typical of AR selected population except A. Occurrence in variable environments. B. High intrinsic rate of growth. C. Onset of reproduction at an early age. D. Extensive parental care of offspring. The presence of all of the following tend to increase species diversity except LA. Competitive exclusion. B. Keystone predators. Scent. Patchy environments. D. Moderate disturbances. The sum total of an organism's interaction with the biotic and abiotic resources of its environment is called its A. Habitat. B. Logistic growth. Scent. Bio-DLC potential. D. Ecological niche. Life sciences admin. K6. Q7. Qs. Co. Kio. Q1. Q12. Q13. Ecology. Which of the following statements about succession is correct? A. Secondary succession occurs where no soil exists. Primary succession occurs in areas where soil remains after a disturbance be sent. Secondary succession can occur where a disturbance has left soil intact. D. Some cases of succession involve facilitation, a phenomenon in which local species inhibit the growth of newcomers. What is the fundamental difference between matter and energy? A. Matter is cycled through ecosystems, energy is not. Energy is cycled through ecosystems. Chapter 08 Evolution. 8.1 Origin of Life. Theory of SPONTANEOQUS Gen. Chapter 08 Evolution. 8.1 Origin of Life. Theory of SPONTANEOQUS Generation, ABIOGENESIS. Abiogenesis is the generation of life from non-living matter. Abiogenesis, now more precisely known as spontaneous generation. This theory states that complex living organisms are generated from decaying organic substances, e.g., organism like mice spontaneously appear in stored grain or maggots spontaneously appear in meat. Francesco Redi, an Italian physician, was the first to disprove the theory of spontaneous generation by performing a controlled experiment. In 1668, Francesco Redi performed an experiment to check whether maggots really came from decaying meat. He did this by placing meat in a number of jars and covering half of them with fine gauze while leaving the others uncovered. Maggots developed only on the meat in the uncovered jars. From this, Redi concluded that the maggots did not come from the meat, but from tiny eggs that flies had laid on the meat. Since flies could not land on the meat in the covered jars, they could not lay eggs on that meat, and no maggots formed. Therefore, decaying meat could not produce maggotae. Later, Lazzaro Spallanzani, an Italian naturalist, performed a similar experiment with broth. He put broth into 2 glass flasks and sterilized them by boiling the flasks containing broth. One of the flasks was left open to the air. The other flask was sealed up to keep out any organisms that might be floating in the air. Microorganisms developed only in the uncovered flask. From this, Spallanzani concluded that the microorganisms did not come from the broth, but were in the air that entered the flask. Broth heated flask left open growth. Figure 8.1. Sterilized broth in open flask. Developed microbes whereas in sealed flask microbes not developed. Broth heated flask sealed no growth. Unfortunately, many scientists were not convinced by his experiment. Louis Pasteur, a French chemist who finally disproved the theory of spontaneous generation in the mid-1800s. He performed the same type of experiment as Spallanzani. Louis Pasteur, however, allowed air to enter into the flask of sterile broth. He performed experiment with 2 flasks, one with straight neck and other with S-shaped neck. Flask with a straight neck allowed both air and microorganisms to enter, whereas the other flask with S-shaped neck allowed only air to enter but not microorganisms. The broth in the straight neck flask became contaminated with microorganisms, but the broth in the flask with a S-shaped neck did not become contaminated. Therefore, Louis Pasteur showed that even though air could get in the flask, the broth did not produce microorganisms. 437. Life Sciences Admin. Weight. No growth. Figure 8.2. Name microbial growth. Occurs in flask with a S-shaped neck whereas microbes growth occurs. Boil break stem * microbial growth in flask with broken stem. Scientists finally were convinced that living things, no matter how small, do not come from non-living things. The present theory of where living things come from is called biogenesis. This theory states that fighting things come only from other living things. For example, mice come only from mice, and microorganisms such as bacteria can only come from other bacteria. Since spontaneous generation was now proved incorrect, many scientists began to wonder how life started on Earth. The Earth formed about 4.5 billion years ago. It is very difficult to determine life's origin because it began at least 3.5 billion years ago. But the preparation for life had to begin a long time before, i.e., some 4.3 billion years ago. Million of years after, under the influence of internal terrestrial heat and solar radiation, the first molecule capable of reproducing themselves in favor catalytic reactions emerged. This crucial event could have occurred 3.8 billion years ago, but in which condition was this prebiotic soup cooked? A. Iaparen attempted to answer this question. Chemical evolution. The spontaneous generation debate heated up again in 1924 when Russian biochemist A. Iaparen proposed that life had arisen from simpler molecules on the lifeless Earth under much different atmospheric conditions than exist today. However, instead of life arising subtly, as previous spontaneous generation theories proposed, Apern believed that it occurred over a very long period of time. Apern and Haldane, working independently, proposed a theoretical model for chemical evolution. The Apern-Haldane model suggested that under the strong reducing conditions, theorized to have been present in the atmosphere of the early Earth between 4.0–3.5 billion years ago, inorganic molecules would spontaneously form organic molecules, simple sugars and amino acids. In 1929, English biologist J.B.S. Haldane published a paper in which he proposed that ultraviolet light, acting on a primitive reducing atmosphere containing water, ammonia and methane, produced oceans with the consistency of a hot dilute soup containing the building blocks of life. Haldane's theory is most famous for its reference to the hot dilute soup of the early Earth. In 1953, Stanley Miller, along with his graduate advisor Harold Urey, tested this hypothesis by constructing an apparatus that simulated the Apern-Haldane, early Earth. Miller-Urey experiment. The Miller-Urey experiment, a classic experiment, fundamentally established that Earth's primitive atmosphere was capable of producing the building blocks of life from inorganic materials. It established that the conditions that existed in Earth's primitive atmosphere were sufficient to produce organic molecules like amino acids. 438. Life Sciences Admin. Evolution. Tungsten. 5-liter flask. Figure 8.3. Apparatus for simulating the synthesis of organic compounds on the prebiotic Earth. A mixture of gases thought to resemble the primitive Earth's reducing atmosphere is subjected to an electric discharge to stimulate the effects of lightning, while the water in the flask is refluxed so that the newly formed compounds dissolve in the water and accumulate in the flask. Condenser. AR. In 1953, University of Chicago researchers Stanley L. Miller and Harold In 1953, University of Chicago researchers Stanley L. Miller and Harold C. Urey set up an experimental investigation into the molecular origins of life. Their innovative experimental design consisted of the introduction of the molecules thought to exist in early Earth's primitive atmosphere into a closed chamber. Methane CH, hydrogen H, ammonia NH, gases were introduced into a moist environment above a water-containing flask. To simulate primitive lightning discharges, Miller supplied the system with electrical current. After a few days, Miller observed that the flask contained organic compounds and that some of these compounds were the amino acids that serve as the essential building blocks of protein. Using chromatological analysis, Miller continued his experimental observations and confirmed the formation of amino acid section glycine, alanine, aspartic acid, glutamic acid, beta-alanine hydroxy acids, and other organic compounds alkylurea, lactic acid, glycolic acid, succinic acid, proprom C acid. Thus, the Miller-Urey experiment demonstrated how some biological molecules, such as simple amino acids, could have arisen abiotically, that is through non-biological processes, under conditions thought to be similar to those of the early Earth. Condensation and polymerization. Miller and Urey demonstrated the formation of simple biomolecules. But the further chemical evolution would depend on the polymerization or condensation of these monomer into polymer, i.e., formation of macromolecules like polypeptides, polysaccharides. For example, nucleic acid bases can be synthesized under supposed prebiotic conditions. In particular, adenine is formed by the condensation of HCN, a plentiful component of the prebiotic atmosphere, in a reaction catalyzed by NH. The other bases have been synthesized by similar reactions involving HCN and H0. Sugars have been synthesized by the polymerization of formaldehyde CH0 in reactions catalyzed by divalent cations, alumina, or clays. It is probably no accident that these compounds are the basic components of biological molecules. They were apparently the most common organic substances in prebiotic times. Proteinoids, thermal proteins. In the 1950s, Sidney Fox and co-workers, University of Miami, produced synthetic peptide-like products of molecular mass between 4,000 and 10,000 Daltons by heating a dry mixture of amino acids at 150 degrees Celsius to 439. Life Sciences Admin. FUIULIUIN. 80 degrees Celsius, which he called proteinoids. Unlike the linear proteins produced by cells, proteinoids are branched polypeptide chains. Proteinoids exhibit several properties similar to biological proteins, including catalyticity and susceptibility to digestion by protease enzymes such as pepsin and trypsin. Region of organized structure I. Complex molecules were produced from simpler ones, how might the have become organized into cells? Macromolecules aggregate into membrane-enclosed droplets, conservatiges in microspheres, as a result. Macromolecules aggregate into membrane-enclosed droplets, conservatiges in microspheres, as a result of intermolecular forces, which exhibit some features of living systems such as organization, selective permeability, and energy use. OASERVATES. Osorbate, term introduced by Apern, is an aggregation of colloic Al particles in liquid phase that persists for a period of time as suspended membrane droplets. Formation of cosorbates occur when dispersed allyl particles separate spontaneously out of solution into droplets because of special condition of acidity, temperature and so on. Cosorbates show a number of interesting properties, able to exchange substance with environment. Can increase in size. Selectively concentrate compounds within them. IICROSPHERES, molecular aggregates of proteinoids. Ox showed that microscopic membrane-bound spheres, termed microsphere, formed when proteinoids reboiled in water and allowed to cool. The microspheres are uniform II in size, stable in double membrane to underscore T appear somewhat cell-like, and can undergo fission and T-udding. Some cell-like properties, UCH's osmosis, growth in size, and selective absorption of chemicals have been ascribed to them. Spontaneous self-assembly of macromolecules into coacerbates, and microspheres indicates that the currents of similar structure under primitive conditions would probably give rise to more organized structure, protocells. Later, protocells that could reproduce would be acted on by natural selection, which rolled act as a creative force successively enhancing the probability of advantageous molecules, reaction and destructure. Lembranes defined the first cell. One of the crucial events leading to the formation of the first cell must have been the development of a neuter membrane. The need for containment is easily fulfilled by a class of molecule that has the simple isochemical property of being amphipathic, that is, consisting of one part that is hydrophobic water W soluble and another part that is hydrophilic water soluble. When such molecules are placed in water, Hay aggregate, arranging their hydrophobic portions as much in contact with one another as possible and their hydrophilic portions in contact with the water. Amphipathic molecules of appropriate shape spontaneously aggregate to form bilayers, creating small closed vesicles whose aqueous contents are solated from the external medium. All present-day cells are surrounded by a plasma membrane consisting of amphipathic molecules, mainly phospholipids. Presumably, the first membrane-bound cells were formed by spontaneous assembly of phospholipid molecules from the prebiotic soup, enclosing a self-replicating mixture of RNA and other molecules. It is not clear at what point in the evolution of biological catalysts and protein synthesis this first occurred. In any case, once RNA molecules were sealed within a closed membrane, they could begin to evolve in earnest as areas of genetic instructions. They could be selected not merely on the basis of their own structure, but also according to their effect on other molecules in the same compartment. 140. Life Sciences Admin. Evolution. Gases of the primitive Earth atmosphere. CO, NH, CH, HCN, HO. Heat or other forms of energy plus water. Amino acids. Heat anhydrous conditions. E. S. Proteinoids. Water. Protocellus. V. Mild heat. Replication of protocells. Energy storage retrieval mechanism, ATP. Photosynthetic. Internal protein mechanism, synthesis. Nucleic acid synthesis, EHRME-OMEAT. Protoribosomes. Genetic coding mechanism. Contemporary cells. Figure 8.4, outline of the major steps postulated for the origin of modern cells. Current models. There is no true, standard model for the origin of life. But most currently accepted models build in one way or another upon a number of discoveries about the origin of molecular and cellular components for life, which are listed in a rough order. Or another upon a number of discoveries about the origin of molecular and cellular components for life, which are listed in a rough order of postulated emergence. The prebiotic conditions result in the creation of certain basic small molecules, monomers, of life, such as amino acids demonstrated in the Miller-Urey experiment by Stanley L. Miller and Harold C. Urey. Plus phospholipids can spontaneously form lipid bilayers, a basic component of the cell membrane. The polymerization of nucleotides into random RNA molecules might have resulted in self-replicating ribozymes, RNA world hypothesis. E-selection pressures for catalytic efficiency and diversity result in ribozymes which catalyze peptidal transfer, hence formation of small proteins, since oligopeptides complex with RNA to form better catalysts. Thus the first ribosome is born, and protein synthesis becomes more prevalent. Propanes outcompete ribozymes in catalytic ability, and therefore become the dominant biopolymer. Nucleic acids are restricted to predominantly genomic use. AA1. Life Sciences Admin. Evolution. Evolution of the cell. The earliest cells probably arose about 3.5 billion years ago in the rich mixture of organic compounds, the primordial soup, of prebiotic times. They were almost certainly chemoheterotrophs. Primitive heterotrophs gradually acquired the capability to derive energy from certain compounds in their environment and to use that energy to synthesize more and more of their own precursor molecules, thereby becoming less dependent on outside sources of these molecules, less extremely heterotrophic. A very significant evolutionary event was the development of photosynthetic ability to fix Colorado into more complex organic compounds. The original electron hydrogen donor for these photosynthetic organisms was probably H, S, yielding elemental sulfur as the byproduct, but at some point cells developed the enzymatic capacity to use H, 0 as the electron donor in photosynthetic reactions, producing O. The cyanobacteria are the modern descendants of these early photosynthetic O producers. One important landmark along this evolutionary road occurred when there was a transition from small cells with relatively simple internal structures, the so-called prokaryotic cells, which include the various types of bacteria, to a flourishing of larger and radically more complex eukaryotic cells such as are found in higher animals and plants. The fossil records show that earliest eukaryotic cells evolved about 1.5 billion years ago. Details of the evolutionary path from prokaryotes to eukaryotes cannot be deduced from the fossil record alone, but morphological and biochemical comparison of modern organisms has suggested a reasonable sequence of events consistent with the fossil evidence. Three major changes must have occurred as prokaryotes gave rise to eukaryotes. First, as cells acquired more DNA, mechanisms evolved to fold it compactly into discrete complexes with specific proteins and to divide it equally between daughter cells at cell division. These DNA protein complexes called chromosomes become especially compact at the time of cell division. Second, as cells became larger and intracellular membrane organelles developed. Eukaryotic cells have a nucleus which contains most of the cell's DNA. Enclosed by a double layer of membrane, the DNA is thereby kept in a compartment separate from the rest of the contents of the cell, the cytoplasm, where most of the cell's metabolic reactions occur. Finally, primitive eukaryotic cells, which were incapable of photosynthesis or of aerobic metabolism, pooled their assets with those of aerobic bacteria or photosynthetic bacteria to form symbiotic associations that became permanent. Some aerobic bacteria evolved into the mitochondria of modern eukaryotes, and some photosynthetic cyanobacteria became the chloroplasts of modern plant cells. 8.2They_ORIESOE Evolution. What is evolution? Biological evolution, simply, is descent with modification. Evolution is technically defined as a gradual process in which something changes into a different and usually more complex or better form. As it is most famously used, evolution is the process by which an organism becomes more sophisticated over time and in response to its environment. Evolution helps us to understand the history of life. Misconception: evolution is a theory about the origin of life. Evolutionary theory deals mainly with how life changed after its origin. Scientists try to investigate how life started, e.g., whether or not it happened near a deep sea vent, which organic molecules came first, etc., but these considerations are not the central focus of evolutionary theory. Regardless of how life started, afterwards it branched and diversified, and most studies of evolution are focused on those processes. 442. Life Sciences Admin. Evolution. LAMARCKISM. Jean-Baptiste de Lamarck, French biologist, published the first truly mechanistic theory of evolution in his book Philosophie zoologique called The Theory of Use and Disuse of the Inheritance of Acquired Characteristics according to this theory. 1. The ecological conditions in which an organism lives causes it to have certain needs. 2. These needs are met by modification of old organs or by production of new rudimentary organs. 3. By continual use of these rudimentary structures, they increase in size and functional capacity, and by disuse they may degenerate and become lost. 4. Character changes brought by the environment during the life of an individual become hereditary and thus can be transmitted to the next generation. A driven by an inner need, be the modified heredity C after many generations of. A short-necked ancestor of the ancestor of such behavior, descendants stretches to feed on leaves manifested by slightly all have much longer necks. High in a tree, the use of longer necks in its. The neck changes the animal's offspring. Heredity according IY. Figure 8.5, example of the evolutionary concept of acquired characteristics. Example, Lamarck would say that cave fish are often blind because their ancestors have lived for several generations in dark conditions, and in each generation the eyes have progressively degenerated through lack of use. The long neck of the modern giraffe could also be explained by the Lamarckian theory. During times when food was scarce, the short-necked ancestors needed to stretch their necks to get leaves higher up in the trees. In this way they stretched their necks. In each generation, the exercising of the neck in this fashion caused an increment in the length of the neck, which become genetically fixed. Lamarck's theory may sound plausible, but it is unsupported by any unequivocal scientific evidence.